5 years after scientists released 1 million microscopic coral babies onto a dead reef, they went back to check on them. What they found wasn't just survival. It was something almost nobody working on this project had actually predicted would happen this soon. The corals hadn't just grown. They'd matured, survived a bleaching event that should have killed them, and started reproducing entirely on their own. So how does a patch of reef go from completely lifeless to making its own babies again in just 5 years? And what does that actually tell us about whether we can outrun what's happening to reefs everywhere else on the planet? To understand what these researchers actually pulled off, you first need to understand one of the strangest natural events on the entire planet, something most people have never heard of, even though it happens every single year. Once a year, an area of coral roughly the size of Italy releases sperm and eggs at exactly the same moment. It's called mass coral spawning, and it was only formally discovered and documented back in the 1980s by a marine biologist named Peter Harrison and his colleagues, a discovery that completely reshaped how scientists understood coral reproduction. Timed by a combination of water temperature and the lunar cycle, usually a few nights after a full moon in October or November, corals across enormous stretches of the Great Barrier Reef release tiny bundles of eggs and sperm into the water column, all within the same narrow window of just a few nights. Divers who've witnessed it describe the ocean turning into something that looks like an underwater snowstorm. Millions upon millions of these bundles drift upward together, rupture, and mix in the open water, creating one of the largest synchronized reproductive events of any species on Earth. It's a beautiful, almost overwhelming spectacle. But it's also, in a strange way, remarkably inefficient, and that inefficiency turns out to matter enormously for what happens next. Most of those fertilized eggs never actually become new coral. Most of them just drift away and die. Currents and waves scatter the resulting larvae in every direction, and only a tiny fraction ever happen to land somewhere solid enough and clean enough to settle and grow. On a healthy reef, packed with enough adult coral to produce billions of larvae each year, that inefficiency doesn't matter much. Sheer volume compensates for the odds. But on a reef that's already been devastated, with only a handful of surviving adult colonies left to spawn in the first place, that same inefficiency becomes a serious problem, a kind of vicious cycle where a dying reef simply can't produce enough larvae to ever meaningfully recover on its own. And by the middle of the 2010s, huge sections of the Great Barrier Reef were in exactly that position. In 2016, the reef experienced what was, at the time, the worst coral die-off ever recorded there. Researchers surveying the northern section of the reef, a stretch spanning roughly 700 kilometers, found that shallow water corals across that entire region had lost an average of 67% of their coral cover in under a year, driven by an extended marine heat wave that pushed water temperatures well beyond what most coral species can tolerate. For decades, the standard fix for damaged reefs was something called coral gardening. It has real limits. Coral gardening involves taking fragments of healthy adult coral, growing them in underwater nurseries, and then physically transplanting those fragments back onto a damaged reef. It works, to a point, but it's slow, it's labor-intensive, and critically, it doesn't restore genetic diversity, since every fragment is essentially a clone of the parent colony it was cut from. On a reef that had lost the vast majority of its adult corals entirely, gardening alone was never going to be enough to rebuild anything close to a self-sustaining, genetically diverse population. So in 2016, Professor Harrison decided to try something nobody had attempted on this scale before. Rather than transplanting adult fragments, his team, working with the Great Barrier Reef Foundation, set out to actively assist the reef's own natural spawning process, collecting eggs and sperm during the annual mass spawning event, concentrating and fertilizing them under controlled conditions, and then delivering the resulting larvae directly onto degraded sections of reef before they had the chance to simply drift away and die like most of them naturally would. The pilot trial happened at Heron Island, and it produced over 1 million coral larvae in a matter of days. Working through the November spawning event, the team collected vast quantities of eggs and sperm from the surrounding waters, reared the resulting larvae in floating enclosures for about a week to give them time to develop, and then released them onto specific damaged reef patches using underwater mesh tents designed to keep the tiny, free-swimming larvae concentrated in the exact spots where researchers wanted them to settle. 8 months later, the team went back to see if any of it had actually worked. What they found were more than 100 surviving juvenile corals, newly established directly on the settlement tiles laid out across the trial site. The first time researchers had successfully accelerated the formation of new coral colonies on the Great Barrier Reef using larvae settled directly onto damaged reef rather than transplanted adult fragments. But the real proof came from something almost accidental: the untouched control sites nearby. Right alongside the treated areas, researchers had left comparable patches of degraded reef completely untouched, with no larvae added at all, specifically to measure how much natural recovery might have happened anyway without any intervention. The difference turned out to be stark. In the treated sites, new coral colonies were visibly establishing and growing. In the untouched control sites, virtually nothing changed. No meaningful natural recruitment happened there at all, years after the original damage. Left alone, that patch of reef simply wasn't coming back on its own. The team returned to Heron Island again for the following year's spawning season and repeated the process. Backed by new funding from the Australian government, the team used the same technique during the November 2017 spawning event, once again producing millions of coral larvae and successfully observing new settlement on the reef, confirming that the first year's results hadn't just been a fluke. By 2020, researchers went back to check on the very first coral babies from that original 2016 trial. What they found were healthy, well-established colonies of branching Acropora coral, one of the reef's key structural species, now large enough that researchers believed they were approaching sexual maturity themselves. In the untouched control sites from that same original trial, researchers noted, once again, that coral communities there had remained essentially unchanged, with virtually no natural recruitment having occurred in the years since. Then, in 2021, something happened that even the research team hadn't fully expected yet. Researchers revisited 22 of the largest coral colonies growing at that original 2016 restoration site around Heron Island, and during that year's spawning event, those same colonies, the ones grown entirely from larvae that scientists had deliberately delivered onto a dead patch of reef 5 years earlier, released their own eggs and sperm for the very first time. A brand new generation of coral larvae, produced naturally by corals that had themselves only existed because of a laboratory-assisted intervention half a decade earlier. This was the first time a fully self-reproducing coral population had ever been established this way. Not just surviving, not just growing, actually completing an entire natural reproductive cycle on their own, meaning this tiny, deliberately seeded patch of reef had crossed the threshold from being a managed restoration project into something capable, at least locally, of sustaining and expanding itself without further human help. And there was another detail buried in that same result that mattered just as much. Those same 22 colonies had already survived a significant coral bleaching event somewhere along the way, one severe enough to have wiped out plenty of coral elsewhere on the reef, and they'd come through it intact, healthy enough to reach maturity and spawn regardless. For a restoration technique this young, that kind of resilience wasn't guaranteed. It was, by the team's own account, a genuinely thrilling result. Word of the Heron Island success spread quickly through Australia's broader reef science community. By 2018, the technique had scaled up dramatically, moving well beyond a single small trial site. A much larger operation, funded jointly by the Australian and Queensland governments, launched off the coast of Cairns, targeting the Vlasov and Arlington reef systems, an effort researchers at the time described as the most ambitious attempt yet to regenerate a reef using this exact method, harvesting millions of coral eggs and sperm during a single spawning event to produce and deploy an entirely new generation of coral larvae directly onto damaged reef. Even the scientists behind this breakthrough were careful never to oversell what it could actually accomplish. Professor Harrison himself repeatedly cautioned that this technique, however promising, was never going to single-handedly save the Great Barrier Reef on its own. It's a tool for accelerating recovery on specific, targeted patches of damaged reef, not a solution capable of outpacing the broader forces, warming oceans, ocean acidification, and repeated mass bleaching events that keep putting entire reef systems under pressure in the first place. That caution turned out to be well placed. The reef kept getting hit again in the years that followed. Since that original 2016 bleaching event, the Great Barrier Reef has experienced multiple additional mass bleaching events, forcing restoration researchers to essentially race against a climate that keeps generating new emergencies faster than any single project can fully repair the damage from the last one. That race eventually pushed Australian researchers to look for ways to make the larval technique itself far more efficient. Scientists at Australia's National Science Agency, working alongside Southern Cross University, developed a new tool called a larval seed box, essentially an underwater nursery and delivery device designed to hold coral larvae in place longer, delaying their natural dispersal and dramatically improving how many of them successfully settle onto a targeted patch of reef rather than drifting away and being lost, the same fundamental inefficiency problem that had limited natural coral recovery in the first place. In an early large-scale trial at Lizard Island in 2024, the results were almost hard to believe. Coral settlement rates in that trial came in up to 56 times higher than what previous restoration methods had typically achieved, across an area spanning thousands of square meters of reef habitat. A leap in efficiency that could dramatically change how much reef this technique is realistically capable of restoring in the years ahead. By 2026, this entire approach had grown into something far bigger than one research team's project. Australia's broader Reef Restoration and Adaptation Program, one of the largest coral reef research and development efforts anywhere in the world, deployed nearly 500,000 newly settled coral babies across sections of the northern Great Barrier Reef in a single season, an operation that pulled in tourism operators, commercial fishing crews, aquaculture specialists, and indigenous ranger groups, whose traditional knowledge of these exact reef systems stretches back generations. According to the program's own operations coordinator, that kind of collaboration is exactly what scaling this work requires. Traditional owner groups bringing generations of deep ecological knowledge about specific reef systems, paired with industry partners contributing specialized technical expertise, working together on an operation that would have been far beyond the reach of a small university research team working alone back in 2016. But not every part of this story points cleanly toward optimism. Some recent research raises real doubts. A 2025 study, conducted by researchers examining coral restoration projects on a global scale rather than just in Australia, found that roughly 1/3 of coral restoration efforts worldwide were ultimately ineffective and unlikely to scale up to meaningfully impact reef systems as a whole. Restoration science is still young, still experimental, and still, by most honest accounts within the field itself, nowhere close to being a guaranteed fix for what's happening to coral reefs globally. So where does that actually leave a project like the one that started at Heron Island in 2016? It leaves it as proof of concept rather than proof of solution. A patch of dead reef that scientists managed to bring back, not just to survival, but to full, self-sustaining reproduction, using a technique that barely existed a decade earlier. It's real, measurable, and it worked exactly the way researchers hoped, arguably faster than most of them expected. But it's also a tiny fraction of a reef system stretching across more than 2,000 kilometers of coastline, one that keeps absorbing new damage from marine heat waves faster, in most years, than any restoration project can realistically keep pace with. Which raises the actual question worth sitting with here, long after the video ends. If a handful of scientists, working with a fraction of a percent of the reef's total area, can turn a genuinely dead patch of coral into a self-reproducing population within 5 years, what does that tell us about how much of this damage is actually reversible, given enough time, funding, and coordinated effort, versus how much of it we're simply going to lose no matter how good these techniques eventually become? Take a look at what's on your screen right now for more on how this same technology is being applied to reefs beyond Australia. Subscribe if stories like this one, real science with real uncertainty still built into it, are the kind of thing you want to keep seeing.